Welcome back to the deep dive. Today, we are strapping in for a bit of a conceptual rocket ride. It's one that might fundamentally change how you view energy, matter, observation itself, really.
Yeah, absolutely.
We're taking an intense look into the origins of quantum reality.
That's right. And when you look at this incredible stack of sources we have here, you realize we're charting one of the biggest, most significant paradigm shifts in human thought ever.
Hmm,
We're moving away from that comfortable, predictable, sort of clockwork physics of Isaac Newton.
right, the classical stuff.
Exactly. And diving headfirst into the weird, probabilistic world of quanta. It's a realm where, well, nothing is certain. Things seem to exist only as possibilities until, we actually look at them.
Okay, so our mission today, let's try and nail this down, is to quickly grasp the core concepts behind this whole transformation.
Yep.
We need to understand the arguments, the experiments that forced physicists to accept that light isn't just a wave, but also a particle, and what this revolutionary idea of quantization actually means for energy, and maybe wrap our heads around why there are these fundamental limits on what we can actually know.
It's definitely ambitious for one session, but the material put together for us by our listener, Fiziko Thritmeni Hachiveli Turunen, it really lays out the case beautifully. It highlights those key experiments, the failures that basically forced this complete reboot of physics.
Okay, let's unpack this then. Where better to start than, where every physics student starts, that great scientific clash, wave versus particle.
Right. We really have to begin way back in 1704 with Newton. He believed light was made of tiny particles, almost like little bullets. He called them corpuscles.
Corpuscles, yeah.
And this view, it was pretty elegant for the time. It explained simple things like light bouncing off a mirror, reflection, and even some polarization effects. For quite a while, that particle view was dominant.
But then the 1800s rolled around and the wave argument just completely took over, didn't it?
It really did. Thomas Young's famous double slit experiment was key. It showed light creating these interference patterns. Bright and dark bands after passing through two tiny slits.
Yeah, you only get that kind of pattern when waves overlap, when they interfere constructively or destructively.
Precisely. Particles just wouldn't do that. If you shot particles through two holes, you'd just expect two distinct clumps on the other side.
Makes sense.
And then the wave view was completely cemented, really, in 1862. James Clerk Maxwell came along with his electromagnetic theory. He described light mathematically as a continuous electromagnetic wave. For decades after that, the wave theory of light felt like, well, a done deal, case closed.
Okay, so if the classical physics of Newton and Maxwell was working so well, explaining so much, what broke it? What was the problem that was so stubborn, so intractable, that it demanded this radical shift in thinking?
The breaking point, the big one, was the problem of black body radiation.
Black body radiation,
Yes.
right? The light and heat given off by a perfect radiator when it gets hot.
Exactly. And classical wave theory predicted something completely absurd. It predicted that a hot object should emit an infinite amount of energy at high frequencies in the ultraviolet range. People called it the ultraviolet catastrophe.
Infinite energy. That clearly doesn't happen.
Yeah, obviously not. So the classical framework, this continuous wave idea, just failed completely when you tried to apply it accurately to heat and light at different temperatures. It couldn't explain the experimental data.
And this is where Max Planck comes in, around 1900, right? To solve this specific mathematical problem with black body radiation, he didn't just tweak the old theory.
No, he did something desperate, something completely revolutionary for the time. He basically had to assume that energy itself wasn't continuous,
Yeah.
that it couldn't just take any value.
Which brings us to quantization, this core idea.
Yes, quantization. It means that certain fundamental properties in nature we already knew about electric charge, for instance, aren't smooth like water flowing from a tap. Instead, they come in distinct, indivisible packets or units. Like currency comes in cents or pennies, there's a minimum amount. Planck proposed that energy, too, must be quantized. It's restricted to specific minimum chunks.
So like you said, energy isn't a smooth ramp you can just slide up and down. It's more like a staircase. You can only be on step 1 or step 2 or step 3, nothing in between.
That's a great analogy, yes.
But why don't we notice this? Why doesn't the world feel jerky or granular if energy comes in steps?
Well, think about heating something up. Like the difference between maybe a low temperature flame, say 450 degrees Celsius, versus a hotter campfire at 500 degrees, the energy needed to make that change, it happens in these discrete steps. And this is the key. The steps are incredibly, incredibly tiny.
Ah, okay.
We just don't perceive them in our everyday macroscopic world because the fundamental unit of energy change is minuscule.
And this minimum unit, this step size, is governed by that fundamental equation of quantum mechanics. E equals hf. Energy equals Planck's constant times frequency.
That's the one. And that constant, H Planck's constant, that's the crucial factor. It's about 6.6 times 10 to the minus 34 joule seconds. It's an unbelievably small number.
Right, 10 to the minus 34. Tiny.
Extremely tiny. That's why reality feels continuous to us. The granularity, the individual energy packets are just too small for our senses or even most everyday instruments to detect directly. It really took those super precise experiments at the end of the 19th century to even hint that energy wasn't smooth.
Okay, so these discrete energy packets, specifically for light, they got a name, didn't they?
They did. They're called photons, the quanta of light.
Photon.
And these photons, they're massless. They always travel at the speed of light, and each one carries a specific amount of energy defined by that equation, E h f. So suddenly, light is behaving like a particle again, which seemed to directly contradict that wave theory that had been so successful.
So wait, if light is particulate again with these photons, does that mean the wave theory, all that work by Young and Maxwell was
Not exactly wrong, no. More like incomplete, fundamentally incomplete. The really definitive proof that light also acted like a particle came a few years after Planck, with Albert Einstein.
Okay.
In 1905, he used Planck's idea to explain something called the photoelectric effect.
Right, that's where light hitting a metal surface can knock electrons out of it.
Exactly. And this effect, it's not some obscure lab phenomenon. It's the fundamental principle behind, well, digital camera sensors, solar panels. Lots of modern tech relies on it.
What's so amazing here, though, is how badly the classical wave theory failed to explain this photoelectric effect. What did the old wave model predict that turned out to be completely incorrect?
Well, the classical wave theory made two main predictions, and both were wrong. First, it assumed that the intensity of the light, how bright the wave was, should determine the energy of the electrons knocked out. More intense light, more energetic wave, should mean faster electrons.
Okay, that sounds logical from a wave perspective. And the second prediction?
The second was that there should be a time delay. The idea was that the electrons in the metal would need some time to sort of soak up enough energy from the continuous light wave before they could build up enough energy to escape.
Right, like filling a bucket slowly with a hose.
Kind of, yeah. But the actual experimental results were completely different and really quite startling at the time.
Okay, so what did the experiments actually show?
Three key things completely defied classical expectations. First, and maybe most surprisingly, electrons were only kicked out if the frequency of the light's color was above a certain minimum threshold value, specific to the metal.
Frequency, not intensity.
Frequency. So you can shine really bright red light, low frequency on the metal all day long, and absolutely nothing would happen, no electrons emitted.
Wow.
But if you used even very dim violet light, high-frequency electrons started popping out instantly.
That is genuinely mind-bending. Brightness doesn't matter for whether electrons come out, only the color, the frequency does.
Exactly. Second finding. The emission was instantaneous. As soon as that high-frequency light hit, electrons came out. No measurable time delay at all.
No soaking up energy needed.
None. And the third crucial finding.
Go on.
The maximum kinetic energy of those electrons, how fast they were moving after being ejected, depended only on the frequency of the light, not its intensity or brightness.
So higher frequency light means faster electrons.
Yes, more intense light just meant more electrons were emitted per second, but each one had the same maximum energy determined solely by the light's frequency.
Okay, that explains things like solar cells responding instantly to sunlight and why only certain colors, certain frequencies work for certain materials.
Precisely, and Einstein's 1905 explanation just nailed it, using Planck's photon concept. He said, forget the continuous wave idea for this interaction. Think of it as a one-on-one collision.
A particle hitting a particle.
A single photon hits a single electron. The photon gives its entire energy packet, EHF, to that electron in one go.
All or nothing.
All or nothing. If the photon's energy, or HF, isn't enough to overcome the energy binding the electron to the metal, that threshold energy, then nothing happens. No emission, like the red light example. But if a photon does have enough energy, high frequency, like violet light, the transfer is instant. The electron absorbs the HF, uses some of it to break free from the metal, and any leftover energy becomes its kinetic energy, making it fly off.
And that perfectly explains why the electron's energy depends only on frequency and why it's instantaneous.
It tied it all together perfectly. This was the definitive proof that light, in this interaction at least, behaves like a stream of particles, of photons.
Was it accepted immediately?
Not universally, no. There was skepticism. But the American physicist Robert Millikan performed very careful experiments over the next decade or so, and he confirmed Einstein's equation with remarkable precision around 1916. That really cemented it, and eventually led to Einstein's Nobel Prize.
Okay, so now we have this massive conceptual problem. Experiments like Young's double-slit scream wave, interference patterns, diffraction, classic wave behavior.
Yep, undeniable.
But the photoelectric effect screams particle, instantaneous frequency-dependent energy transfer, classic particle behavior.
Also undeniable.
It seems like light is both. How is that even possible? This sounds like the ultimate paradox, wave-particle duality.
And that's exactly what it is. This is where we have to abandon that comfortable, classical, binary thinking of it's either A or B.
Right.
Quantum mechanics forces us into this strange Bocan territory. Light is both a wave and a particle.
Yeah.
Which aspect you see depends entirely on the kind of experiment you perform.
And this duality, it wasn't just limited to light, was it?
No, that was the next radical step. Louis de Broglie, a French physicist, proposed in the 1920s that if light waves can act like particles, then maybe particles like electrons, protons, atoms, everything can act like waves.
Wow, okay, so matter itself has wave properties.
That was his hypothesis. He even derived a relationship for the wavelength of a particle, connecting its momentum, p, to its wavelength, lambda. Lambda equals h divided by p Planck's constant again, linking the particle property momentum to the wave property wavelength.
And this wasn't just theory. Was there experimental proof for matter waves?
Oh, yes. Experiments quickly confirmed that electrons, for example, could produce diffraction and interference patterns, just like light waves. Electron microscopes rely on the wave nature of electrons.
So this duality applies to everything.
Fundamentally, yes. Though for macroscopic objects like us, or a baseball, the momentum is so large that the de Broglie wavelength is astronomically small, completely undetectable. But for subatomic particles, the wave nature is significant.
Okay, let's go back to that double-slit experiment. But now imagine we're firing electrons through it one by one. What happens?
Okay, this is where it gets truly mind-bending. If you just fire electrons through the slits and detect where they land on a screen behind it, over time, even though each electron arrives as a single dot, a particle, the pattern that builds up is that classic wave interference pattern, bright and dark fringes. Each electron seems to somehow know about both slits, like a wave passing through both simultaneously and interfering with itself.
Even though it's just one electron going through at a time.
Even then, it behaves like a wave when you're not looking, so to speak. But here's the kicker.
Okay.
The moment you try to detect which slit the electron actually goes through, maybe put a little detector by one of the slits.
Yeah, to see which path it took.
The instant you make that measurement, that observation, the interference pattern, vanishes completely.
Vanishes? What do you see instead?
You just see two distinct bands on the screen, exactly where you'd expect particles to land if they went through one slit or the other. The electron stops acting like a spread-out wave and behaves like a localized particle the moment you observe its path.
So the very act of observing it forces it to choose being a particle.
It seems that way. It's as if the electron exists in a state of wave-like potential, passing through both slits until the measurement forces it into a definite state, a definite path, behaving like a particle.
That is just incredible. It really drives home that idea of complementarity you mentioned, maybe like the yin-yang symbol. You need both wave and particle aspects for a complete description, but you can only ever observe one aspect at a time, depending on your experiment.
Exactly. It's not that it is a wave or is a particle. It has the potential to be either, and the measurement determines which potential becomes reality.
This observation-dependent nature, it must have profound philosophical implications, right? If what we see depends on how we look, what does that say about an objective reality independent of us?
It plunges us right into the deep end, philosophically speaking, and it leads directly to another cornerstone of quantum mechanics, Werner Heisenberg's uncertainty principle.
Ah, yes, the uncertainty principle. Often misunderstood, I think. People sometimes think it just means our measuring tools aren't good enough.
Right, like it's just a practical limitation of measurement error. But it's far more fundamental than that. Heisenberg showed it's actually a law of nature.
Okay, so what does it fundamentally state?
It states that it is fundamentally impossible, not just difficult, but impossible to simultaneously know both the exact position, let's call it the uncertainty position delta x, and the exact momentum, uncertainty delta P of a particle with perfect accuracy.
You can know one well, but not both.
Precisely. There's a trade-off. The more precisely you determine the particle's position, making delta x very small, the less precisely you can possibly know its momentum, delta P becomes large, and vice versa. There's a fundamental limit given by the equation delta x times delta P is greater than or equal to a constant related to Planck's constant h bar.
Can you give a sort of intuitive reason why this isn't just about clumsy measurements? Why is it baked into nature?
Well, think about how you'd measure the position of something incredibly small, like an electron. You have to interact with it, right?
Yeah, you have to see it somehow, maybe bounce light off it.
Exactly. Bounce a photon off it. But that photon, even a single quantum of light, carries energy, EF, and momentum, p lambda. When it hits the electron to reveal its position, that collision inevitably transfers some momentum to the electron, changing its velocity in an unpredictable way.
Ah, so the act of measuring position inherently disturbs the momentum.
Right. And if you try to use a lower energy, lower momentum photon to disturb the momentum less, that photon will have a longer wavelength. A longer wavelength means you get a fuzzier, less precise measurement of the position. You can't win.
It's an inherent trade-off built into the very act of measurement at the quantum level. You cannot observe without fundamentally disturbing the system you're observing.
That's the core insight. It's not about building better instruments. It's about the nature of interaction itself at this scale.
This just completely shatters the old classical dream, doesn't it? Newtonian mechanics basically promised a clockwork universe. If you knew the exact position and momentum of every particle at one instant, you could predict the entire future perfectly.
Absolutely. That was the deterministic ideal. But quantum mechanics, through the uncertainty principle, says flat out, you cannot know the initial conditions perfectly. Therefore, perfect prediction is impossible. Reality at its most fundamental level involves inherent uncertainty, probability, indeterminacy.
Wow. And this limit on perfect knowledge, it isn't just confined to the quantum realm, is it? The sources connect this to chaos theory as well.
That's a really interesting connection, yes. Chaos theory, developed much later, deals with complex systems in the macroscopic world, things like weather patterns, fluid dynamics, population growth.
The stuff Edward Lorenz worked on, the butterfly effect.
Exactly. What Lorenz and others discovered is that even in purely classical deterministic systems, if they are complex enough, they can exhibit extreme sensitivity to initial conditions.
Meaning a tiny, almost immeasurable change at the start can lead to wildly different outcomes later on.
Precisely. The flap of a butterfly's wings in Brazil could theoretically set off a tornado in Texas weeks later. Not because of the energy of the flap, but because that tiny perturbation gets amplified exponentially through the complex nonlinear interactions in the weather system.
So even if we ignored quantum uncertainty, even if we could measure the initial state of the atmosphere almost perfectly, chaos theory says we still couldn't predict the weather accurately very far into the future.
Correct. Because any tiny error, any imperfection in our initial measurement, and there will always be some imperfection, gets blown up over time, making long-term prediction fundamentally impossible for chaotic systems.
So we have limits on prediction coming from two different directions.
Kind of. Quantum mechanics tells us perfect knowledge of the initial state is impossible at the micro level due to fundamental uncertainty. Chaos theory tells us that even near perfect knowledge isn't enough for long-term prediction at the macro level for complex systems due to sensitivity. Both point towards a universe that is inherently less predictable than we once thought. Probability rules, not certainty.
What an incredible arc. Seriously. We've gone from the absolute certainty of light being just a wave to Planck's sort of desperate but necessary idea of energy packets, the quanta.
Right, solving the black body problem.
Then Einstein using those quanta, the photons, to definitively explain the photoelectric effect, proving the particle nature.
Yep, nailing that down.
And finally landing in this strange world of wave-particle duality, complementarity, and the fundamental uncertainty principle that governs reality itself.
It really is a journey through one of the most profound shifts in scientific understanding. The material we covered really walks us through why that shift had to happen based on experimental evidence. It forces us to accept a universe that operates on probability and chance at its core.
And that leaves us, and leaves you, the listener, with maybe the most provocative thought to chew on. If the very nature of reality, whether something manifests as a wave or a particle, seems to depend on whether we're looking on our active measurement, what does that actually imply about the existence of an objective reality that's just out there, independent of us when we aren't looking?
That's the question, isn't it? It's something physicists, philosophers are still grappling with today. What is the nature of reality before the measurement? Does the question even make sense?
Something to definitely keep exploring.